Good morning.
How's it going? It's okay.
Pretty good. We're almost at the break.
I
Yay. And it's
know.
in person.
What?
Then we're in person, right?
Well, yeah, that's true. That's true. Things will get very interesting very quickly. Because we're in physics class and physics is going to get really interesting. So, to get started, what I want you to do is I want you to quickly think about what you remember about the centripetal force. Just quickly jot down as much as you remember. You may want to look at your notes and see what you remember about it. We'll take a few minutes for people to gather and figure out, well, not figure out, uh, write down what they think or they remember the centripetal forces, what their own personal knowledge about centripetal forces. But yeah, we'll take a few minutes for people to edit. So for those of you just joining us, take a look at your notes if you have to. But what I want you to do is I want you to think about what you remember about the centripetal force, and then in chat you can message me or you can message the class. What do you remember about the centripetal force? What do you think it is? What do you think it involves? What do you think it does? Take another minute or so. And then it's one about. Just start writing out what you remember about the centripetal force, and then about in a minute or so, I'm going to tell you to hit enter, and then we'll all see what everyone has to say. Just take another minute and a half. What do you remember about the centripetal force? What do you think it does? What do you think it involves? Right, in 15 seconds or so, whatever you've written down. Get ready to hit enter. 5, 4, 3, 2, 1. Hit enter. Whatever you have to say about the centripetal force, I want to hear. What do you remember? What do you think it involved? So it's the force that makes the objects accelerate. Oh boy. I was about to, you know, that feeling when you're like about to sneeze, but then you don't actually sneeze. Okay, so centripetal force, it's the force that makes the object accelerate towards the center of a circle. This isn't a real force, it's actually more of a net force. The force that pushes and accelerates a car to the middle of a circle and allows it to turn. A force directed towards the center when an object is moving in a circle. It's not a real force, but an emergent one through different forces acting upon an object in a circular motion. As a centripetal force is the net force that pulls. Centripetal force is the net force that pulls someone to the middle of the circle, which allows an object to turn. The centripetal force acts on a body moving in a circular path and is directed towards the center around which the body is moving. It's not actually a real force, but it's usually the result of combined forces that include gravity, friction, and the normal force. Various forces combine and contribute to the centripetal force. Wow, I couldn't say it any better. So what is the centripetal force? Centripetal force, it is indeed the force that pushes and accelerates the car to the middle of the circle. What I like about what everyone has sort of said is, oh, disappeared, slide disappeared. What I like about what most people said about the centripetal force is that it's an imaginary force. It's not a real force. What I like about the centripetal force, it's an imaginary force. It's not a real force, and it pushes and accelerates a car to the middle of a circle. So if the car is going around in a circle, right, or in a turn, there's a radius of that circle, and then the centripetal force is pushing it to the middle of that circle. What most people said is that it's the centripetal force. It's an imaginary force, which is very important because there's no force itself called the centripetal force. What you have to remember is that it's actually more of a net force. So when a car is going around in a circle, there is an overall net force pointing the car into the middle of the circle. And you have to think about what forces combine to constitute the centripetal force. So usually forces that might interact to produce a centripetal force might include gravity, friction, and the normal force. I think tension can sometimes be involved too, depending on the problem. But those are the forces that usually might interact. I mean, it's kind of ironic because those are the sort of the 3 or 4 forces that we've only learned so far. So yeah, so the forces that we learned so far, they can all potentially contribute to the centripetal force, depending on the context of the problem. So it's very important. Because even within the same scenario, the different forces can change. What contributes to the centripetal force can change just depending on the situation in the problem. So it is kind of weird. But again, the most important thing is it's more of a net force. It's not a real force. So if you're drawing a free body diagram, you don't want to be drawing a centripetal force because again, it's not a real force. You'll have to think about what force is actually contributing to the centripetal force. So as a recap of what the mathematical result of centripetal force is. So if the centripetal force, you could you can calculate it through the equation mv squared over r, where v squared over r is your centripetal acceleration. So notice how this seems very similar to our equation F equals ma, and in this case, our acceleration is indeed v squared over r. So it's more of a specific case of your net force equation. So basically, what happens is that if your car is going around in a circle with a radius r at a certain velocity v, you need a certain amount of centripetal force in order to make the car go around in that circle. And then so the various forces in the problem will add up to equal the centripetal force if the car is successfully going around a turn. I mean successfully because if the car does not have enough centripetal force, it won't be able to go in a circle. It'll either slide out of the turn or yeah, so it won't be able to go around in a circle if there isn't enough centripetal force. And yeah, it's mv squared over r. So basically the net force on a car in a circle is your centripetal force, and that's equal to mv squared of r, which is the force you need to make it go around in a circle. So what I want you to do right now is I just want you to do a very quick problem here. What I want you to do is I want you to figure out what is the amount of centripetal force that this particular car experiences. So this car is 100 kilograms. It has a mass of 100 kilograms. It has a radius of 10 meters and it has a velocity of 20 meters per second. So what is the centripetal force that this car experiences? Just be pretty quick, pretty straightforward. The hardest part is trying to figure out what force do you think produces this centripetal force. So figuring it out mathematically is not that hard, right? Because you just plug in mv, v, and r. But what's hard is going to be what force do you think produces this centripetal force? Because it's very important to identify which force produces this centripetal force, because sometimes you need to do it the other way around. You need to figure out how much centripetal force is in the problem through your forces. So take a few minutes to figure out the mathematical amount of centripetal force that the car is experiencing. And what force do you think, what physical force do you think is contributing to this centripetal force? So what force do you think is producing this centripetal force? Take another minute or two. So I think finding it mathematically is pretty straightforward. I think everyone can get it. The hardest part is trying to figure out which force is actually producing the centripetal force. And so what I'm going to be doing once I sort of working through it is to try to draw it out and see if we can make sense of it. So for now, I'm just going to quickly, just do the math part first. So the centripetal force that any object is experiencing is its mass plus squared r. And so in this case, it's 100 squared r to the 10. So that one too hard. The harder part is, I think, trying to figure out which force is actually producing the centripetal force. Okay, so let's say hypothetically the car is going around a circle like this. Let's say the car is here. So what we're wanting to do is we're going to want to kind of draw a free body diagram of the car. So we're not going to look at the car. So sorry, this diagram makes it seem like it's a top-down view. But we're instead going to look at it as like a normal free body diagram point of view, where the force of gravity is going straight up. No, the normal force is going straight up. Straight down. And this is going to look kind of weird because it makes it look like the normal force is taking forward, force of gravity taking backwards. But really, this is meant to be more up-down. So the normal force is going straight up, and the force of gravity is going straight down. This is pretty standard because the force of gravity always pulls the car into the ground, and the normal force is needed, provided by the ground, to keep the car from falling through the ground. The question is, what force is producing this force? Well, if the car is going around a circle like this, right, that means you essentially need a centripetal force that's going like this. So you need a centripetal force that's going to the middle. And right now, based on the forces we have, this normal force right here is going up, this gravitational force is going down. So none of these forces can contribute to my centripetal force, right? Because I need a force going to the middle, and this normal force is going up, and this gravitational force is going down. So I need another force here as a problem to provide a centripetal force. This, in this case here, is actually going to be the force of friction. The friction in the tires is actually providing a centrifugal force that pushes the car into the circle. So the normal force here and the force of gravity here are both not providing anything with centrifugal force. Your force of friction here is the only one providing. So what you could essentially say is you could say that the centrifugal force is 4,000 newtons. You could also say that the force of friction is also 4,000. Does anyone have any questions about why the friction force might be pushing the car in? I think that's probably the hardest part, really, is trying to figure out what force is pushing it in. Okay, so as we continue our discussion of centrifugal force, another way you can think about it is that the net force on acting on an object is equal to the centrifugal force acting on an object, which is equal to the sum of all forces acting on an object, which is equal to mv squared over r. So they all basically mean the same thing here, right? If a car is going around in a circle, the net force acting on it is centrifugal force acting on it, which is the sum of all forces acting on it, which is mv squared over r. Okay, so the thing is, what I want you to notice here is that, right, in this case here, your force has your centrifugal force has a direct relationship with your velocity and an inverse relationship with your radius. So that means if you're going very, 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 very fast, your velocity is squared, right? Which means that you're going to need a lot of centrifugal force in order to push you around in a circle. So the faster you're moving, the more centrifugal force you need to push you in a circle. Now, if the forces involved in the problem aren't enough to generate enough centrifugal force, then you won't be able to move around in a circle. For example, a 1 kilogram car traveling at 1 meters per second around a turn of 1 meters, that's going to need 1 Newton of centrifugal force to push the car into the middle of the circle in order to make a turn successfully. However, if the friction from the road can only generate 0.5 newtons of force into the middle of the circle, then that car won't be able to make the turn because the centrifugal force needed exceeds the amount of centrifugal force able to be generated from the road. So the car won't be able to make the turn. What will probably happen is the car will slide in some way or another. It'll either just like really, like if you remember when I was playing Project Cars on Tuesday, if you remember what happened when I tried to make a turn really quickly, that's really unfortunate. I'm sorry. That's really unfortunate. So if the car is if there isn't enough centrifugal force, the car won't be able to make the turn, and it'll start like sliding out, or just end up going in a straight line. So it won't be able to make the turn. So either some other force will have to provide your centrifugal force. Either some additional force is needed to provide your centrifugal force, or it just won't be able to make the turn. Additionally, if you also notice that the wider the turn is, the less centrifugal force you need, which makes sense, right? If you're trying to go around in a very sharp turn, it's very hard to do that, which is because you need a lot of centrifugal force available in order to push the car around in such a tight turn. However, if you're going around in a very wide turn, you don't need a lot of centrifugal force. You could just take your time going around it. So the next thing I'm going to talk about a little bit is the concept of G-forces. We will use G-forces, I think, maybe in, I think we'll be using G-forces a good amount, not so much in the beginning, but we will use G-forces quite a bit later on. So what is a G-force? You probably have heard of a G-force before, at least once in your life. However, you may not know exactly what it means. You probably know that it's something that a person might feel if they're in a fighter jet or in a plane or in a car or in a roller coaster or something. I think some of you even told me something about G-forces on Tuesday. So what G-forces are, it's just really just another way of measuring acceleration. It's sort of like, you can think of it as it's like another unit for acceleration. So another way of measuring acceleration, and this is particularly true in circular motion or anything that's going up or down or stopping and starting really quickly. And that's to measure acceleration in terms of G-forces. So what is particularly misleading about this is that a G-force is actually a measure of an acceleration. It's not actually measuring the force. So G-force is not a force, it's actually an acceleration. Yes, the G-force, you can think it's actually more of a G acceleration versus a G-force. So what a G-force is you're basically comparing the acceleration of the force or forces you are experiencing to the acceleration due to gravity. So let's say you are in a jet or whatever, in a roller coaster or whatever, and you are experiencing a net force of you're experiencing a G force of 1. That means you are experiencing an acceleration of 9.8 meters per second squared, which is just 1 times G, right? Let's say you are in a different part of the coaster, and so now you are experiencing a G force of 2. That means you are now experiencing an acceleration of 2G, or 19.6 meters per second squared. A G-force of 3 means that you are experiencing an acceleration of 29.4 meters per second squared, which is 3G. Not 3G in that's terms of the cell phone tower, but 3G in terms of gravity. And so on and so forth. The more G's you're experiencing, the more acceleration you have. On the flip side, if you are, let's say, accelerating at 4.9 meters per second squared, that means you're experiencing a G-force of 0.5 G. So it's really just a measure of acceleration. It's really just more of a way of comparing how fast you're accelerating to that of the acceleration due to gravity. Yeah. So the reason why G-forces are particularly interesting and important is because you use G-forces when you measure the acceleration of a person that is going around in a circle or going up or down or even left or right very quickly. So it's basically just imagine if you're changing your velocity really quickly, that's generally what you use, what G-forces are used to measure. So this is particularly relevant in stuff like aviation, car collisions, roller coasters, rockets, centrifuges, anything that's like you feel where you're feeling a lot of force really quickly. That is where G-forces are being used to measure. So the reason why G-forces are important is because there is a limit to how much G-force a human body can tolerate. So what happens if your body has experiencing too much of a too much G-force? That means that can happen as you can black out, you can lose vision, you can lose consciousness, or you could possibly even die if you're experiencing too much G-force. So in general, in a typical scenario, I think humans can. The weird thing about G-force is that the amount of G-force your body can tolerate, it depends very much on the direction you're going. So your body cannot experience a lot of G-force going up or down very quickly. I think it's something like less than 10 Gs. So your body can't experience a lot of G-force going up or down. It instead can experience a lot more G-force going left or right really quickly, quite a bit more. In fact, I believe one of the highest G-forces ever recorded is that of a person who was in the Indianapolis 500. So it was a car race, and he was involved in a car collision. I don't know if he hit a wall or he hit another car, but he hit another car, and so the G-force he experienced was 200 G. So the acceleration he was experiencing was 200 times the gravity, which if you do the math, that's 2,000 meters per second squared, which is very, 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 very fast. And he experienced 200 Gs of acceleration. Luckily, he did survive, which is kind of ridiculous because that is a very high acceleration. But yeah, so a lot of times what happens is if you're like in aviation or if you're testing something, you will measure how much G-force that particular thing is producing, because you need to figure out if the human body can actually tolerate it, because otherwise they might black out or lose vision or something. Yeah, so another thing that's kind of interesting that G-force is that if you're in a jet or in a rocket or something, the suits you wear actually help help increase your body's tolerance for G-forces. One of the reasons why G-forces is why it's so hard on the body is because when your body is experiencing a lot of G-force, what it means is I don't really I have to think about it, but like it basically means that blood is not going to go to certain parts of the body. I think if you are I think usually it's because your brain is not getting enough blood. If you are in space and are not near a gravitational field, can you experience more G's? If you're in space, you actually experience less G's because you're basically like that's what the feeling of weightlessness is. You're basically feeling no acceleration at all, which is why we feel weightless. So you're actually experiencing 0 G. So if you're in space and not near a gravitational field, if you're in space and near something like that's very massive, so if you're near something like Jupiter or if you're near something like the sun, you're going to experience a lot of G's, a lot of G's. I mean, if you're in a spacecraft, yes, if you're in a spacecraft, you can experience a lot more G's. That's if your spacecraft is accelerating. So one of the things about, so this is actually really interesting because the theory of relativity has a lot to do with this. Has a lot to do with the idea of accelerating and non-accelerating frames of references. This is all getting very like technical very quickly. Are G specifically the strength of Earth's gravity? It's basically you're comparing the strength of the acceleration to that of Earth's gravity. Yes. So you are comparing the strength of whatever acceleration you are feeling to that of Earth's gravity. So theoretically, we could set G to be the Mars's gravity, and it would get a different number, but the concept is the same. However, because we live on Earth, it makes the most sense to set all of our G's to that of Earth's gravity. So if you are in a spacecraft, like one of the things that happens a lot, that's probably one of the weirdest thought experiments is that if you are a rocket that's accelerating upwards at 1 meters per second, 1 G, so 9.8 meters per second squared, is there any difference between that and that of Earth's acceleration? And the answer is that no, you actually won't be able to tell the difference if you are in a spacecraft or if you were on Earth, if the acceleration you were feeling were the same. That's kind of weird to think about. So yeah, so that's one of the reasons why one of the challenges of space exploration is that you need to, if you want to go somewhere far, you need to go very fast. However, the twin paradox, yes, the twin paradox. The twin paradox is a very real thing. So what's one of the challenges of human exploration in space is that you need to go very fast, which generally involves a lot of very fast acceleration, which is very hard on the human body, which requires a lot of things to to deal with it. Until the spaceship disintegrates as it approaches light speed. If the spaceship can get anywhere close to light speed, I think we would be very happy. The fastest, I believe, thing we've produced is the Voyager 1 spacecraft. And I think it had a maximum speed, I think of 70,000 miles per hour or something. And that's because it was slung around it was basically going through several gravitational fields, and it was basically it was like a slingshot. It was basically going around one planet, getting slung out, going on another planet, getting slung out. And so it was going something like 70,000 miles per hour, which sounds pretty fast, except when you compare it to the speed of light, it's kind of a complete joke. So it's nowhere even close to that of the speed of light. So unfortunately, we as humans have not produced anything capable of taking us to the speed of light. What was it? So what was I talking about? Oh, I was talking about. Yes. So the reason why humans can't experience a lot of G forces is because when you're experiencing a lot of G forces, the blood in your body is going to get pulled in different locations. The reason why up-down G forces are the hardest on your body is because your brain is the one that's losing blood, whereas if you're going left to right, your brain isn't losing blood. And so what happens is a lot of if you're in like a jet or if you're in a rocket or something, the suits you're wearing are specifically designed to help keep blood in your brain. So that way, when you're experiencing a lot of this G forces, your brain isn't losing blood. So that helps increase the amount of G force you can experience. Additionally, you can actually undergo training, like fighter pilots and astronauts and stuff are actually trained to tolerate more G forces than the average human being. So they can actually tolerate stuff up to like 9 Gs in the vertical direction, whereas the average human being would probably only be able to experience something like 5 Gs. But yeah, Gs are cool. G forces are very cool. Maybe we'll do some more stuff with G forces. I think that's probably one of the most interesting things about forces is G forces. Well, G acceleration. Where you get my gist. Okay, so does anyone have any question about G forces? Anything that's particularly interesting? We have the twin paradox, which is really interesting. I could talk about that for like, easily 5, 10, 15 minutes. I don't know if we want to talk about it today, but the twin paradox is really interesting. It has a lot to do with relativity. Relativity is probably one of the weirdest things you'll ever encounter. So I'm going off on a tangent here. So the special relativity, yes. So basically, let me put it this way. So as of right now, I've told you that gravity is a force. However, some of you are aware on your force data analysis, I actually wrote to you that gravity is not actually a real force, which is weird. The way we're doing our class is we're doing a Newton's approximation of gravity. So basically, for most cases, we can approximate gravity as being a force, and we can approximate it with a certain relationship. However, what happens is that once in certain scenarios, the Newton's laws of gravity, the Newton's approximation of gravity breaks down and it stops working. And so this is especially apparent in stuff like so a lot of times we actually have to use special relativity to make more accurate predictions for gravity. So one of the problems with the way GPS systems work is that you have multiple satellites that are triangulating. They each are essentially triangulating your position to help you to identify your exact coordinates. However, one of the main issues with the GPS system was that if you're using Newton's approximation of gravity, what happens is that gravity actually, oh God, I don't even know how to try to explain this, but gravity actually slows down. Oh God, I feel like I'm just like butchering this because it's such a complicated topic and I feel like I'm just like butchering it. But basically, gravity does really weird things. If you're accelerating, it does some really weird things. And the faster you're going to the speed of light, the weirder things get. Yeah, so it's called special relativity and even general relativity. Yeah, so TED, Ed, and Minute Physics. The fighter jet, the amount of G's that could produce could kill a human. Black hole singularity, am I a joke to you? Yeah. TED, Ed, and Minute Physics both have great videos on the twin paradox. Yeah. Oh God, special relativity is so cool though. It's really cool though. If you ever want to major in physics, you'll start learning about it. Okay, so I digress. I've clearly went on to a tangent. Some of you are probably very upset with me. So we're gonna bring us back into centripetal force, centripetal acceleration with a practice problem. So in this particular problem here, what you have is a motorcycle that's being driven around a 12-meter tall vertical track. It's basically going imagine if your roller coaster was going in a loop. Well, instead of a roller coaster, you're actually going around in a instead of a roller coaster, you're going around in a motorcycle. And in this particular case, you have a motorcycle that is driven around a 12-meter tall circular track at a constant speed of 11 meters per second. So once again, what I want you to do is I want you to find the magnitude of the centripetal force, which is not too complicated. However, the harder part is figuring out what forces are actually constituting the centripetal force. So what forces are actually producing this centripetal force? So we'll take a few minutes to work through this. To figure out what the centripetal force is, what are the magnitudes of forces.
It's like a couple minutes and then I'll start working through it. So once again, I don't think the math part of this problem is that complicated. But the harder part is trying to figure out what force or forces are actually constituting the centripetal force. So once again, let's take a look at this problem here. I think what we're going to do is we're going to first just start with the math part. I think that part is more straightforward. So first off, how do you find these centrifugal force? The formula for centrifugal force is in this case, M is 250, B is 11, is oh no, B R 12. Sorry. And so this would mean that our centrifugal force is 1. So whatever forces we have that are acting on this problem needs to produce a centrifugal force I/41. So the math part, not too hard. The problem is what forces are actually contributing to this. So these are 3 body diagrams you can figure out what's going on. So in this case, the motorcycle is sort of going around clockwise, essentially. So first off, as usual, force of gravity goes straight down. I think R is 6, not 12. Yeah, you're right. Right? Does that mean I did my math? Yeah, I think you get the number right. Yeah, it's okay. So for example, the diameter of the loop is 12, the radius of the loop is 6. Yes, you're right. Okay, so the number is still the same, it's still 5,400. So the force of gravity on this particular object points straight down. However, that does not help us at all
Because the object, right, if the object is going around a circle like this, we need a centrifugal force that goes like this. Like this. So, and as you can tell, our gravity here does not contribute anything at all to our centrifugal force. So what could possibly be contributing to our centrifugal force? Well, here's what I want you to notice. The motorcycle is resting. So let's get a very in-depth view of this part, right? So the motorcycle is resting on the track, so it's touching the track. And as the track is also touching the motorcycle. So the motorcycle is going to be pushing against the track. The track is going to be pushing against the motorcycle. So because the two objects are in contact with each other, that means that there's going to be normal force behind them. So in this particular case, the track is going to push the normal motorcycle into the middle. So the force is producing a centrifugal force is the normal force. Because, and this is weird because most of the time, I think we almost understood that inhabited force of gravity upside down, sort of drill that into. This is where we need to start breaking down this simplistic idea and instead about something a bit more realistic, which is the known force, the direction of the surface is acting on the object. In this case, here, it's perpendicular to the surface, so it's simple now. They're not in the same plane. So in this case, the normal force is actually producing an entirety of my centrifugal force. So in this case here, my normal force is just the equal. Does anyone have any questions about this one?
Do we not consider the applied force here?
Where would the applied force come from?
From literally just, I believe it's a motorcycle. So, because
So
we
let's say
see.
motorcycle is applying an engine force, while the engine force would be going forward. So even if we consider the applied force here, it still wouldn't contribute anything to these.
Okay.
Okay, so let's take a look at the next problem. The next problem is a little bit more complicated. So yes, the problem is different. It is different. It looks very similar. It's different. But this time, instead of looking at the left side, we are actually looking at the top. So I. So when the motorcycle is at the top of the loop, what forces constitute the centrifugal force? And so what are the magnitudes of the forces here? So this time the motorcycle is at the top of the loop instead of the side of the loop. So what forces will constitute the centrifugal force? And what would the magnitudes of these forces be? So I'm going to take a look at this problem here. I think this one is kind of interesting. So first off, the first thing I want to say is that the centrifugal force of this problem is still the same. Still 5,480. So we don't need to recalculate this because the object is still moving at the same velocity and it still has the same radius and still has the same mass. So nothing about the centrifugal force is the same. However, the one thing we can't assume is going to just be the same is the fact that the forces acting on this will create this, the forces that are creating this centrifugal force are the same. We can't assume that. So what we're going to do is mainly try to identify what forces are actually contributing to my centrifugal force in this case. So in this particular case, now we're actually looking at the motorcycle when it's at the top. And so we need a centrifugal force that is going to the middle. So what forces are producing our centrifugal force? So first off, as always, force of gravity is always going to go straight down. So is that it? Are we done? Well, I think we're still forgetting one thing. Once again, the motorcycle is still touching the loop, which means that the loop is still touching the motorcycle. So because the loop is touching the motorcycle, it's going to also be exerting a normal force onto the motorcycle. So notice how here, it's really weird, our gravitational force and our normal force are both in the same direction. I don't know if we've ever seen this before. Here, we can show that it's completely the same direction. If I look at it, I don't think there's any other forces here that will contribute to our centrifugal force. So in this case here, we have two forces that are contributing to our centrifugal force. So what we can say is that the sum of all forces acting on the motorcycle is going to be equal to our centrifugal force. Our centrifugal force that we found earlier was 5,041. So the sum of all forces will be equal to 5,001. Now, the forces that we're looking here in particular, but we're going to be looking at the force of gravity. And we're going to be looking at the one. Now, the force of gravity is always m times g. The maximum gravity of the normal force is 1 equal 5,041. Don't remember what m times g is. Okay, so this means that our force of gravity here is 2450 newtons. And then my normal force is going to be 25. The motorcycle is pushing against the track. It is pushing against the track. So yes, if the motorcycle was not pushing against the track, then there wouldn't be a normal force. But the fact that the motorcycle is touching the track means that there is contact. And as long as there's contact, there is a normal force. So I know it's weird because technically the motorcycle is falling. So technically it's not really like. But as long as two surfaces are in contact with each other, there is a normal force present. That's the weird thing. I know it looks like in this case the motorcycle is really pushing against the track because it's like really falling. But the reality is, as long as it's touching the surface, there is a normal force. If it's not touching the surface, there is no normal force. Let's say hypothetically that we're looking at a scenario where maybe the motorcycle was like, instead of touching the loop, maybe it was falling. Well, then there wouldn't be a normal force because it's not in contact. But as long as it's in contact with something, there is a normal force. The two forces are exerting a force onto each other. So yeah, it's weird. I know it doesn't make sense because like when you're sitting on a motorcycle, you're not really envisioning yourself as pushing onto the track. But as long as two surfaces are in contact with each other, there is no normal force. Does that make sense? The fact that there is contact means that there is a normal force. And that idea is actually very important because we will be using it a good amount. Well, not a good amount, we will be using it later on. So one thing that can be helpful for you in terms of identifying what were the forces when it was at position I. So when it was at position I, the centripetal force was created by the, so when it's at position I, the normal force was created by the centripetal force was created by the normal force. And gravity did not be used. So when it was in position II, the normal force produced is the force of 5,000. And your gravitational force contributed nothing to this. When you're in position I, both gravity and your normal force contribute to the centripetal force. The sum of both is equal to 5,000. So when it's on the left, what keeps the bike on the track when it's on position I? Well, here's the thing. The bike is accelerating downwards. Does not mean that it's moving downwards. So the bike is moving forwards. It's accelerating downwards. So because it's moving forward, by the time it's falling, it's already on the next section of the track. And as long as it's, and by the time it's falling faster, it's going to be the next section of the track. So that's the thing here. You need to be essentially moving fast enough so that the rate at which you're falling is not faster than the rate that you are touching the tree. Basically, you need a certain velocity in order to make it successfully through. I don't know if you remember this from the last time. When we played Roller Coaster Tycoon, and I was very upset because I built the first hill too small. And so the roller coaster could be able to go up against the roof. Well, that's because there wasn't enough velocity so that it couldn't go up to escape essentially the pull of gravity. You need to be going fast enough so that you are sort of like, it's like almost like you're racing against time here, right? You're falling at some rate. So you need to be going fast enough so by the time you're falling, you've already moved on to the next section of the track. So there's nothing that's preventing the bike from falling. It's still falling. It's just that because it's also moving forwards, it's still moving contact with the track. That's the thing. There's nothing that's preventing the bike from falling. It is falling. It's just that because it's moving forward, it's able to still touch the track. If it wasn't moving forward fast enough, then it will just fall and everything will just touch. Is there any way to account for inertia in a free body diagram? There's no way to account for inertia because inertia itself is not a force. It's a concept. It's not something you can't calculate inertia. It's just the concept. The concept of inertia is what's keeping the bike essentially going forward, and it's like the concept of inertia that's preventing the bike from falling down. But inertia itself is not a force, and you can't calculate it. So it's like an idea. Not really a mathematical thing. So yes, unfortunately, there's no way to account for it in a free body diagram. And in a free body diagram, you wouldn't even draw this velocity arrow because of how it is. So this is kind of weird because the bike is moving forwards, but it's accelerating downwards. So based off of this free body diagram, you would assume that the bike is slowing. But the only thing that this free body diagram tells us is that the bike is accelerating downward. It does not tell us that the bike is actually. This can't actually tell us whether or not it's taking the track or not. That's something where we have to look at the velocity itself. Does that make sense? Did I answer everyone's questions? I know we had quite a few questions. That's good. It's good to have questions. It means that I'm. Does anyone else have any questions? I'll try to explain them to the best of my ability here. Okay, so that's very nice. Thank you. Okay, so we're gonna skip this one because this one is just basically figuring out how much G force you're experiencing. this is just, essentially calculating the acceleration. What we are actually going to do is we're actually going to look at one more problem here. This problem is, idea is similar, but there's a little bit of a different context. So in this case here, you have a 500 kilogram car and you're entering a turn. So it's very similar to this problem right here, except this time we have a little bit more information. So this car is entering a turn with a radius of 25 meters, and it's entering the turn with a velocity of 15 meters per second. This time though, what we know about the road is that the road has a coefficient of kinetic friction of 0.25. So what we need to do is we need to figure out, will the car be able to make the turn successfully? Will the car be able to make the turn successfully? Oh, yeah. Sorry. My bad. Yeah. So a car is entering the turn with a radius of 25 meters at a velocity of 15 meters per second. The road has a coefficient of kinetic friction of 0.25. Will the car be able to make the turn successfully? So I'm going to just work through this problem here. So once again, we can figure out how much what the centrifugal force is. So this car is attempting to make this turn. So what we need to do is we need to figure out how much centrifugal force we need in order to make the car, in order for the car to make the turn successfully. So the amount of centrifugal force we need is the mass of the car and the velocity of the car squared. So it's 515. 515 squared. This is okay. And now we have centrifugal force. But what does this mean? What does this mean? I found this force, but what does this mean? Like, why do I have this force? Well, this force tells us that in order for this car to successfully make the turn, we have these variables. We need this at least this force provided by whatever force is here to push the car in. So we need a force of 4,500 to push the car in. If the force we have not produced this force, then the car will not be able to go in the circle. So, oh yeah, the classic. We can't see your screen. Classic, Mr. Hu. Okay, so we need 4,500 units of force to find a circle. The question is, can we actually get that much force? So first of all, we have to do the normal force. Let's pick up, down, and in this case, here the force is 30 in the middle. This is similar to the problem. One of the problems we did. So the only force that's contributing to our system. So we need to see, hopefully, if our force of friction is greater than or equal to, or the maximum is greater than or equal to. We cannot friction force produce. So the force of friction here is going to be UK maximum force. Our normal force is this G in this case. We'll figure that out. Look back and down. We'll force it up. You can get it out. So if the maximum amount of kinetic friction is this greater than or equal to? Well, if we work this out, what we get is that the maximum kinetic friction force we are able to get is only 12. So this is the amount of friction force we're actually able to get in the problem. However, we need 4,500. So what this means is that we actually can't make the turn. Can't make the turn. There's not enough friction force available. We need 4,500 pieces of force we found. However, the only force contributing to the friction force when we we're only able to get a force of 12. So in this case, we can't make the turn. So yes, the force you need has to in this case, you need to overcome the centrifugal. You need to essentially have enough centripetal force to do so. I think when it's in a loop-de-loop, I think it's loop-de-loops are different. No, never mind. But yeah. So yes, the idea is that in order to make a turn, you need this much centripetal force. You can't get this if you can't get enough centripetal force, you can't make the turn. So it's 9:55, so that will be it for today and for the week and for a lot of things. So I mean, you don't have any homework because we're not supposed to, but I also think it's unreasonable, and I also think that it's stupid. So no homework, obviously. And then I will have a nice break, and I'll see you guys when we get back. Yeah.
Thank you, Mr. Hu.
Thank you. Have a good break.
Thank you. Have a
Thank
good
you.
break.
Thank you.
Bye. Have a nice break.
Thank you.